Good afternoon, and somehow we got to the last lecture of the course. Looks like it was yesterday we started. So today we're going to have a very relaxed session. So my plan is we're going to have a lecture of about an hour or so, hour and 15. And then those of you who like coffee or tea can join me in the SIPA coffee shop. And I'm going to treat you to whatever non-alcoholic beverage of your choice. I have to abide by the rules. So by 5:30 or so, those of you who want to come over, it's on 118th and Amsterdam. I'm sure you know, right? 6th floor cafeteria. So I'll be there. And come by if you have some time, okay? So that'll be after the lecture. Before that, we'll see a couple of topics. We'll see a bit of spread spectrum, and then we'll see multi-user channels, okay? So we'll touch on these two topics today, which correspond to chapters, I think, 9 and 10 in the textbook. So we'll just touch on some parts of those chapters. Okay, let's first go through a summary of what we saw last week, which was coding. So we saw that coding was essential for reliable communication. We had already seen this in an early lecture about information theory. So as such, coding is an essential ingredient of any digital wireless system. And it allows us to reduce the error probability as long as the rates are below the capacity, at the expense of using complexity and some latency. So we studied mostly block codes, NK binary linear block codes, which convert blocks of K information bits into blocks of N coded bits, where N is always bigger than K. All right, so the rate of the code is actually K over N. And there's two classes of block codes. The systematic ones, where the first K bits of the code words are actually the first K bits are actually the information bits themselves. And then we append, after the K bits, we append N minus K redundancy bits, which we call parity bits. So those are the systematic codes. And they're very common because of this structure that they have, which is quite convenient when you have to actually build the encoder and the decoder. And the non-systematic ones, where all the bits are actually computed as function of the K information bits. Okay? The main measure of distance between code words is the Hamming distance, which measures the number of bits in which two code words are different. And the minimum of all distances between code words is the minimum distance dmin, which is a key parameter in quantifying the error probability of the code. So there are two ways to decode block code: hard decisions and hard decision decoding and soft decision decoding. So remember, in hard decision decoding, the demodulator first makes a decision as if the code didn't exist, so as if the signal wasn't coded, was not coded, just based on distances in the constellation space. And then it feeds these ones and zeros to the decoder, which then groups them into groups of n, and then tries to find the most probable code word. Okay, so that's the hard decision decoding. And the number of errors that we can detect is dmin minus 1. And the number of errors that we can correct is t, which is dmin minus 1 divided by 2. And be careful, because the 2 divides the whole thing. Okay, so there should be a parenthesis here. So it's this whole thing, dmin minus 1 divided by 2. And then if it's not an integer, we just round it down. Okay. Now, an obvious shortcoming of hard decision decoding is that the demodulator discards useful information, which is how far each point in the constellation space was from the actual decision point. So we could have decisions that were very reliable or some that were very unreliable, but once we run them down to zeros and ones, that information is lost. So there is an advantage in preserving that information and giving soft information to the decoder, and that's what we do with soft decoding. Okay, so we pass along the exact point in the constellation space where the received signal lied. So then we moved on from block codes and talked about convolutional codes, which are generated by passing information bits through a linear finite state shift register with capital K stage. And we call capital K the constraint length of the code. Typically is on the order of 7 or 8 in digital wireless systems. And each stage has K bits per stage. So the most convenient representation of convolutional codes is through using trellises, which is a 4 tree. And in the homework, you guys had a chance of working with a couple of trellises in the problem. So hopefully that gave you a chance to familiarize yourself with how they work. The way to decode a convolutional code is also using the trellis, and by tracking finding the most probable path through the trellis. Okay, so this is a pretty hard task because of the large number of paths, and it's drastically simplified by using the Viterbi algorithm that was, as we discussed, invented by in the 60s, 68, I think, the year I was born. So also here we can decode, correct, up to t errors. And t is, again, the distance of the code minus 1 divided by 2. The only difference is that here the distance is called d3 as opposed to dmin. But other than that, it's the same notion. Then we talked briefly about the state-of-the-art encoding, which is embodied by turbocodes, which is a pair of codes that are coupled together through an interleaver. And then they're decoded at the other end iteratively. So the two codes decode their own part of the code, and they pass the information to the other decoder. So they exchange this information back and forth. And on every iteration, the decoding becomes more and more reliable. And these codes are very powerful. They perform very close to capacity. In other words, they allow you to reduce the error rate of signals that are very close to capacity. Okay, as close as a little fraction of a dB, actually, has been demonstrated, like a tenth of a dB. And an essential ingredient is an interleaving. And again, also in fading channels, even if you don't use turbocodes, the interleaving is an essential component of coding to break up the burstiness of the fading. Okay, so that's the role of the interleaver. So that's a bit of a summary of what we saw in coding, and hopefully the homework was useful in getting you guys to practice some of these notions. So any questions on this? Comments that came out of the homework maybe? Okay, so we're going to touch briefly on spread spectrum now, just about 10 minutes or so. Just so you guys have a bit of an idea of what spread spectrum is. So spread spectrum is a digital communication technique that increases the bandwidth of the signal to values much larger than what you need to transmit the information. So that may puzzle you at first, since we discussed in the introductory lectures that bandwidth is very expensive and one has to be very careful, being very efficient with the bandwidth. And in fact, we spend a lot of effort about bandwidth efficiency. So now we're saying, okay, we're just going to use much more bandwidth than we need. Well, there better be a good reason for that. And in fact, there is. There are good reasons. So the reasons are several. First of all, when you use spread spectrum, you can actually overlay users on the same bandwidth. So even though it seems that you're actually wasting bandwidth, you're actually recovering it. For example, that's what they do in CDMA. Okay, so if any of you guys has a Verizon phone, I don't know, does anybody here have a Verizon phone? Okay, so those are CDMA phones. So those use spread spectrum, and they spread the signal by a factor of 64. So they use 64 times the bandwidth that you would need to send the information. Now, in return, you can actually pile up to 64 users, one on top of another, on the same bandwidth, right? So you seem to be losing at first, but then by piling up users, you actually can recover and get back to where you started. So there's no obvious loss of bandwidth, because thanks to the spreading, you can actually pile up users. Okay? So, and I'll tell you a little bit more about that in a couple of minutes. So the bandwidth loss is not real. Then there are other advantages that motivate the use of spread spectrum. Actually, these are the reasons that this stuff came up in the beginning. So the main reasons are eavesdropping protection and jamming resistance. So spread spectrum signals are very hard to intercept. Like if you're just an eavesdropper, they're very hard to actually decode. So they offer a lot of protection. In fact, the spread spectrum techniques are widely used by the military. In fact, all the signals that the military uses is always using spread spectrum for this reason, because they don't want to be vulnerable to jamming, and they want to be protected against eavesdropping. So, for example, GPS, right? Some of you may have GPS receivers for location, right? So those use also spread spectrum signals. Okay, so the signals that come from the satellites are actually spread. Okay, so those are the reasons that we use spread spectrum. There's another reason that is very handy in wireless, which is that because of the bandwidth expansion, we get a lot of diversity. So we take a signal that, for example, you take a Verizon signal, you can send a voice conversation using 10 kilohertz of bandwidth. It's about what you need to send a voice call, right? Now these guys use 1 megahertz of bandwidth, right? Verizon uses 1.25 megahertz per voice call. So that puts your signal over wide bandwidth, which means that some of the signal is going to be faded, but some is not going to be faded, right? Because the fading is going to be changing in frequency. So it's never going to be the case, or very rarely the case, that the whole signal is going to be faded. So usually part of your signal will actually survive the fading. So that offers very good protection against fading in the form of frequency diversity. That's a good benefit, which in wireless is very handy. So there are two ways to spread a signal. One is by so-called direct sequence spreading, which we'll see now. And then later we'll see frequency hopping spreading. Okay, so these are the only two ways in which you can spread a signal. So let's start with direct sequence. That's what Verizon uses. Okay, this is what Verizon uses for their CDMA phones. So here you achieve the bandwidth expansion by multiplying the signal by something called spreading sequence or spreading code. So I'm going to try to depict it here using this picture that I drew over the weekend. And I'm going to use no-pass notation here, or no-pass picture. So the cosines of 2 pi FCT are not here, right? It's just the no-pass signal. Okay, so the carrier signal, the cosine is not here, just the envelope. And I'm just drawing rectangular pulses just because it's easier to draw. Okay, in reality, we know that we don't want to use rectangles, right? Remember we spoke about this a few weeks ago. You want to use Nyquist pulses, right? That are smooth and that don't have edges. Okay, but for simplicity of the diagram, I'm just using it. So keep this in mind. Okay, a real signal will be smooth and a Nyquist. Okay, so I'm using rectangles just to make the drawing simple. So this is your signal, right? It's a bunch of pulses. Say it's a BPSK signal, for example, right? So you have ones and minus ones. Okay, ones and minus ones, and another one, and minus one, and one, and minus one, etc. Right? So now how do I spread it? Well, I multiply it by something called the spreading sequence, which is made, okay, so the signal is made of symbols, right? Each of these rectangles is a symbol. The spreading sequence is made of chips. That's what they call it. Okay, so it's little rectangle here is called a chip. And these chips are much shorter than the symbols. Okay, here they seem to be maybe 8 times shorter. In reality, in Verizon case, there are 64 chips for every symbol. Okay, so this is a very fast signal, and it's a pseudo-random signal. So it's not really random because it can be reproduced, but it looks random. So if you don't know, if you're just an observer, it looks random to you, right? You flip between 1 and minus 1 randomly. In reality, you can actually generate it. There's a polynomial that you can use to generate it. So it's not really random, but it looks random. So that's what they call it, pseudo-random. You have this pseudo-random signal, and you just multiply it out. Okay, so if you do that, okay, this is a 1, right? So these chips are just preserved. Here you have a minus 1, so these chips are flipped over. If you check, you'll see that every sign here is flipped over. Okay? So the pulses that are 1 just carry through all the way. The ones that are minus 1 just flip the corresponding chips. Okay? So that's what you get down here, is the product of these two waveforms. So that's what you do in the case of Verizon. You take your bits after the encoder, modulate them using BPSK, actually that's what they use, and you multiply by a spreading sequence, and you get something like this. And that's what you send out. Now, how do you recover this at the receiver? Anybody? No, you know. Anybody else? How would you recover the signal? So say you know this, right? You know this. You can reproduce this. How? Exactly. You just multiply it again, and what's going to happen? What's going to happen is that the ones are going to become ones, stay ones. The minus ones times minus one is going to become a 1, right? So this whole thing is going to be canceled out. So that's what you do, actually. So first, let's look at what happens in the frequency domain, okay? So this multiplication, right? What's the corresponding operation in the frequency domain, right? When you multiply something in the time domain, what happens in the frequency domain? Anybody? Convolution, right? So the Fourier transformations of the signals are actually convolved, okay? So as you know, roughly, when you have a signal like this, the bandwidth of the signal is roughly the reciprocal of the symbol time, right? So in this case, it's 1 over Ts. The bandwidth of this signal is 1 over Tc, okay? When you convolve two signals, their bandwidths add up, essentially. Okay, so the signal that gets multiplied out has a bandwidth of about 1 over Ts plus 1 over Tc, okay, which is approximately 1 over Tc, because Tc is much smaller than Ts. Okay, so that one dominates. So essentially, you spread the bandwidth by the ratio between Tc and Ts. So for example, as I was saying, in Verizon case, you expand the signal from about 20 kilohertz to 1 megahertz using so it's a factor of 64. Okay, so that's the transmission. The reception is based on multiplying the signal by the same spreading sequence, okay? Which, as I say, is easy to see, right? You multiply this guy by itself, and it becomes just 1 everywhere. So it just cancels, and you get back this signal. Now, there's a very important thing here, right? You have to multiply by the sequence, but it has to be properly lined up. It has to be exactly lined up with the original sequence, right? So you need to have synchronization down to the chip level. It's very important. The receiver has to synchronize its local copy of the sequence down to the position of a chip. Otherwise, the thing doesn't work. So synchronization is very important in these type of spread spectrum systems. In fact, in CDMA systems, the base stations are synchronized using GPS. So Verizon's base stations don't have a GPS. So if somehow GPS stopped working, right now, all the CDMA phones in the world would stop working immediately because they will move the synchronization. They couldn't decode the signals anymore. Okay, so they're synchronized down within a fraction of a microsecond. So if GPS stopped working, CDMA phones would just stop working right away. So synchronization is an essential ingredient of spread spectrum. So, as I said, these sequences are usually pseudo-random, or sometimes they're orthogonal, okay, from orthogonal groups. And I'll show you an example in a little bit. Now, what happens if we multiply the incoming signal with a different spreading sequence, or with a disaligned version of the spreading sequence? Okay, I'll let you answer this time.
But, I can answer this, but I have a question.
Oh, okay, go ahead.
If it goes to 0, right, in theory.
It goes to 0, yeah, or close to 0, yeah.
Yeah. But then you said the synchronization is not done by the pilot system?
Yeah, but the base has to have synchronization, a reference, right? Yes. So okay, it depends. On the reverse link, on the forward link is different. On the reverse link, there used to be no pilot. Now they put them in, but they used to have no pilot in the reverse. Only in the forward link there were pilots. Now they put them in the reverse also. The downlink always has a pilot, right? And then, right, in the pilot, in the downlink, you don't need GPS. In fact, the phones don't have it usually, right? It's the base that needs the synchronization, right? So because what happens is the different bases use the same spreading sequence with a different time alignment. So they need to be time shifted by 64 chips, exactly. So they need to be synchronized within a few microseconds, the bases. And the way they do it is they all drive a reference signal from the GPS satellites. So they all read the same timing signal, right? That's the reason that they need the GPS. Not for location, for timing. Usually for timing. So, but you could probably, you already answered the question also about what happens when you multiply these by a different spreading sequence, right? So imagine that you have another random sequence like this one, but not this one, a different one. Or just this one shifted by some distance, right, by some time. What's going to happen is that if it's really random, if it really moves random, you're going to have a 50% chance of multiplying and getting a 1 or a -1, right? So when you add up over a certain interval, you're going to get about the same number of 1s and -1s. You're going to get something that's very close to 0, okay? Just statistically speaking. And that's what they do, right? So in CDMA, you use different spreading sequences for every user. And you differentiate them using that way, right? You multiply by spreading sequence, you recover the signal of that user, and the other ones essentially give you 0 contribution. Not exactly 0, but small contribution. So by using different random sequences, you can separate different users in a CDMA system. And also, this gives you protection against eavesdropping, right? Because if you don't know the sequence, right? If you don't know the sequence, you cannot possibly decode the signal. There's no way, right? Because it moves random to you. So that's it as far as direct sequence spreading. So any other questions or comments before we? Yes.
If it goes to 0 in theory, there is a sequence with the user 1 sequence and user 2 sequence are not supposed to be aligned.
Well, it goes to 0 if the sequences are orthogonal. Then it can be exactly 0.
The make orthogonal is actually not
if they line up, exactly. So what happens is that usually the pseudo-random sequences, and they have very low correlation, but it's not exactly zero. It's going to be a small number, but not zero. Yes, exactly. Right. So the sequence, essentially, sometimes you use the same sequence, you shift it by some time, and that one is not exactly orthogonal to itself. It's something like, but it's designed to give you a small contribution. So it's supposed to be a small number. Okay, so that was the direct sequence spreading. Now, you can also spread the signal by using frequency hopping. So here what you do is, you just hop around. You have your signal and you just hop around in frequency. So let's look at the picture that's in the book, 13.4. Okay, so imagine this is your signal, right? This is your normal signal. Now what you do is you just jump around, typically every few milliseconds, to different frequency, right? It's the same signal, it just jumps around. And if the receiver knows the jumping pattern, the hopping pattern as it's called, right? It can just track it, right? It knows exactly what it's going to hop next. It just hops to that same frequency, and you can just follow the sequence. If you know what the signal is going to be hopping around, if you know the hopping pattern, then you can actually follow it. If you don't, you're going to lose it, right? So again, it offers good protection against eavesdroppers, just casual listeners. So typically the time between hops is a few milliseconds. And this has its origins in World War II. The hopping sequences, again, can be orthogonal or can be pseudo-random. So if they're orthogonal, you can imagine you have two users, right? Let's go back to the picture. Imagine you have two guys that are hopping around, right? If the hopping patterns are orthogonal, it means they're never going to collide, right? They're never going to be on the same frequency at the same time. They're always going to be avoiding each other, right? If you use pseudo-random hopping patterns, every once in a while, they'll hop on the same frequency, and they're going to collide, okay? With no probability, but it may happen, right? So that's the difference between the orthogonal hopping patterns and the pseudo-random hopping patterns. So again, you can have different users coexisting. They just hop around differently. And if you know the hopping pattern for each of them, you can just decode them. If you don't, you can't. So the overall bandwidth is roughly n over ts, where n is the number of possible frequencies on which you can hop, and 1 over ts is the bandwidth of the signal at each point in time. That is it for spread spectrum. So I think that's enough for what we're going to see now. So any other questions on the spread spectrum, or is the notion clear? Without, we haven't seen any math or formulas here. It's just really conceptual. But okay. All right. So we're going to now get into the last topic of the course, which is multi-user channels. So mostly so far we've analyzed what happens to particular users. Now, in a wireless system, multiple users have to coexist, right? They have to share the channel. So now we'll talk about how that sharing takes place. So there's two types, actually there's more than two, but we're going to talk about two types of multi-user channels, the uplink and the downlink. So the downlink is also called the forward or the broadcast channel, is the one that goes from the base station down to the mobiles. Okay, so it has one transmitter, which is the base station, and multiple receivers, which are the user terminals. Okay. So the power and the bandwidth that the base has must be divided between the different links to the different users. Okay, that's what we're going to be talking about now. In the downlink, synchronization between users is pretty easy because all the signals originate at the base. Okay, so they have the same clock at the base station. They can just be perfectly synchronized at the base because they're generated by the same set of circuits. So that's a very nice feature of the downlink, is that synchronization is very easy in frequency and in time. They have the same oscillator, they have the same clocks, everything, right? The only issue is delay spread in the channel that can distort, that can add some jitter to the synchronization. But other than that, synchronization is not an issue in the downlink. Now the uplink is quite the opposite. The uplink, or the reverse channel, or the multiple access channel, is the one that goes from the mobiles up to the base station. Okay? So we have a bunch of terminals sending data to a common receiver, which is the base station. So here again, the bandwidth must be shared, but now the power is no longer shared. So each terminal has its own battery, its own power supply, right? They don't have to share it. In the downlink, the base has an amplifier that has to be shared for everybody, has a power access that's common. In the reverse, each user has its own battery. So power is not shared, but bandwidth is shared. Synchronization is challenging because users are in different locations, so they don't have access to a common clock reference. And even if they use GPS to get synchronization, they are different distances from the base station, right? So even if the two have the same clock, miraculously, right? And they send the signal at the same time, because one is more far away, it's going to get there later than the other one, right? So the channel itself destroys the synchronization because of the different distances. And also, each user may have a different speed, right? So the Doppler spread of every user can be different. So it is more problematic in that sense. Now, in most systems, we have, of course, both uplink and downlink. And so we have to also separate these two links. So this separation is called duplexing. And there's two ways to duplex. There is time division duplexing and there is frequency division duplexing. So in time division duplexing, what we do is we alternate in time. Okay? So we take our time and we divide it in slots. So we say we have, okay, we have a certain time that's dedicated to the uplink, then to the downlink, okay, then to the uplink, downlink, and so on and so forth. Okay, so we alternate in time. So typically these nodes are a few milliseconds long, right? So for a few milliseconds, the base talks to the mobiles, then it stops. Then for a few milliseconds, the mobiles talk back to the base, then they stop, and then they alternate forever. Okay? That's TDD. And a nice advantage is that if these nodes are very short, the channel may actually stay pretty much constant. You know, the fading may be very flat. And so the base receives on the uplink slot, right? You can learn the channel, estimating it from the signals that come in. And then if the fading is slow, you can actually use that channel when you train it on the downlink. Okay? So you can use this reciprocity. And if you go back to information theory, you can you have CSI at the transmitter, and you can use power allocation, power control. Remember we talked about doing power control when you knew the channel coefficients? So you can do that in TDD because you learn the channel on the uplink slots. And then if it doesn't change too quickly, it's still bounded for the downlink slots. So you can actually use some of those ideas we talked about power control. Remember the water filling and the channel inversion, truncation, all that stuff? You can do it here. Because of, in fact, it's done because of this reciprocity. Okay? That's a nice feature of TDD. Now in FDD, what you have is you have two frequency bands. Okay? In one of them, the uplink is taking place, so the mobiles talk to the base. In the other frequency band, the base talk to the mobiles. And these are continuous. So at all times, these two are going on. One goes up, the other one goes down. Okay? In this case, the fading is different on both channels, so you can use this trick doesn't work anymore. But it has some advantages too. You don't need to be switching back and forth, so the channels are always on. Here they're on half of the time only. So there's some trade-offs here. Now, all the cellular systems that we have commercially today use FDD. Okay, so some of you guys' phones use FDD. This used to be used for not for cordless phones. It's still used for cordless phones, for example, short range. Now there's a big buzz about TDD again for fourth generation. So it's kind of making kind of a comeback also. So we may see systems with TDD in the future, but today everything is FDD. Okay, so let's talk about the uplink in particular. Well, we talk about both, but in the uplink there is something interesting, which is there is two different ways of accessing the uplink. There is multiple access when the access is persistent. So for example, in circuit switch voice, or in packet switch applications with tight latency constraints, you need to have the channel always ready to go, right? So you have a persistent allocation, and you may use it, you may not use it, but it's always reserved for you. So it's kind of a circuit switching idea. And this is called multiple access. Now there is something called random access for access that is sporadic or bursty. So this means that you may not send anything for, I don't know, several minutes, for example. And then you want to send something, right? So that would be a random access type of scheme. And, okay, I'll tell you more in a second. So for now, just introducing the notions. So we'll talk first about multiple access. Okay, so here's for persistent access to the base, and then we'll talk about random access. Okay, so multiple access techniques. There is several ways to access the channel using multiple access. Essentially, you want to partition the available dimensions, signaling dimensions, which are time, bandwidth, and space, mostly. And then you assign portions to different users. So this partition of the resources can be orthogonal or non-orthogonal. So the orthogonal types are two, FDMA and TDMA, okay? Frequency division, multiple access, and time division, multiple access. And then non-orthogonal are CDMA, code division, multiple access, and SDMA. Actually, this can be orthogonal too. This is somewhere in between. Depends on the codes. If the codes are orthogonal or non-orthogonal, okay? So we'll see that in a second. And then there is the one that is definitely not orthogonal, which is the space division multiple access. And then there are hybrids. There are combinations of these. So historically, the oldest multi-access technique is FDMA. So frequency division multiple access. What you do is you just divide your bandwidth into non-overlapping channels. Okay, so say this is the frequency. So what you do is you say, okay, I have one channel here, another channel here, another channel here. You break it up in channels, okay? Each one has some bandwidth. And then you give these channels to different users, and the users are orthogonal in frequency, so they don't interfere with each other. And each one has its own channel, okay? So this is the oldest way of doing multiple access. You need some guard times, some guard intervals between adjacent channels. Okay, so here you need some protection here between the signals, because the filters, you use Nyquist filters, so this has a certain runoff, right? It falls down, right? So there's a certain amount of tails, and you need some separation to ensure that the tails fall off and all that stuff. So there is a certain bandwidth that's wasted in guards. Also, to protect against Doppler, right? Because Doppler is going to spread and move these signals around. So you want to make sure that Doppler doesn't, push one signal onto another one. So also for Doppler, you need some separation. Now, a nice feature of FDMA is that the channels are on all the time, so they're continuous. And actually, it used to be a nice feature, but then at some point it became a drawback. We'll see. So the reason it's a drawback is because it complicates handoff. Remember what handoff is? Handoff is the switching from one base to the other, right? You're talking to a base station, you just move around, and eventually you get far away from that base, you get close to another one, different cell. Okay, so you get handed off to the other base, right? So how does that work? How do you know when to hand off?
Probably when the power is going down.
Yes, exactly. So you need to, the mobile actually measures the signal from other bases, right? And if at some point the signal from another base is much stronger than the one that you're talking to, let's say, I don't know, 3 dB stronger, typically it is 3 to 5 dB, you decide that you've moved close to the other base, right? So that's how it works actually, right? So your phones actually make measurements of all the neighboring bases. And at some point, if one of them is really better than the one that you're talking to, you request a switch, a handoff to that other base, right? Now, to make these measurements, you need to listen to the signals of the other bases, right? Which may be on different frequencies. So if you have to be on all the time talking to your base, right? You have a hard time measuring other bases, right? So you may actually need a second receiver, for example, just to do that job, right? Or you have to abandon your frequency for a little while to measure other signals and then come back to your signal. Right? Imagine that you're this guy, right? You're on this frequency, and you want to listen to other bases which are in different frequencies, just to see if they're stronger, right? So you have to abandon this frequency for a while. And it's problematic if you have to be on all the time, right? So this is a drawback. And your comment? Yeah, you have to abandon your signal for a little while to measure somewhere else. Yeah, yeah. In fact. So once they had handoffs in the systems, this became a throwback, the continuous transmission. But nonetheless, FDMA was using the original analog systems, and it's usually part of all the hybrids. And it can be combined with hopping, right? You can have signals like this, where now these guys are hopping around, right? At least in theory. So the op-amp system, the analog system that we had in the US in the 80s, had 25 megahertz per operator. Like Verizon had 25 megahertz, for example. Actually, Verizon didn't exist at the time. It was Bell Atlantic, but Bell Atlantic had 25 megahertz. And each channel was 30 kilohertz. Okay, so it's 24 for the signal, plus 2 guards of 3 kilohertz on each side, right? So you have 24 plus 3 on the right and 3 on the left. So it's 30 kilohertz in total, right? So if you divide up, you'll see that you could fit about 800 users in that system. Okay, so it's 25 megahertz divided by 30 kilohertz. It's 832. Okay, so that's what you could fit in the old AMP system. Yes? It is 6 kilohertz, right? Yes, it's 6 out of 24, so it's like a 25%, which is a non-negligible overhead. It's significant. So the big competitor to FDMA came in the form of TDMA, where you do the separation in time. So now you have time slots. Okay, so you have you have time divided in slots, and you give the slot to user 1, user 2, user 3, user 4. Okay. So typically you have a combination of these with FDMA, but this is TDMA, and that's what, for example, GSM uses. So those of you that have singular phones or T-Mobile phones, they use TDMA. Okay, so there are 8 slots per channel. So you have 8 users share the same bandwidth by taking turns in time. Okay. So you need some buffering, first of all, right? Because if you are user 1, right, you're here for a while, you have your 2 milliseconds, and then you're off for all this time while the other guys are talking. You come back here, right? Eventually, you come back again. So you have every 8 slot is for you. The other 7 are for some of the users, right? So how do you send voice over here, right? So you need a buffer, right? So you just the receiver just buffers the signal and just makes it continuous again. Okay, so you don't see it transparent to you, but you need some buffering. You need some memory in the receiver to just make this intermittent nature disappear. So you need some buffering, but it has a nice feature that you're on for a slot and then you're off for 7 slots. So in these 7 slots, what you do is you start to make measurements for handoff. And that's what they do, right? So while the other guys are talking, you're actually listening and communicating with the other bases, negotiating handoffs and doing all these other things, right? And then you come back to your traffic channel on the slot 1. So it's a very nice feature that you have this continuity in the signal. Now, a major problem in the uplink is the synchronization, right? Because what happens, okay, so think about the uplink, right? Like, you're user 1, and he's user 2, right? You're very close to me. He's far away, right? Now, you have to send me your signal. It has to arrive in this time interval, okay? He has said his signal has to come in this time interval, right? Now, what happens if, because he's more far away, his signal may be delayed, right? So he has to advance it, right? He has to advance it because, you don't have to advance it because you're right here. He has to advance his signal, otherwise it's going to fall into somebody else's slot, right? So that's what they do in GSM. They have advancement. So the base station, so when you come in the first time, you come with a very short slot, very short. Okay, so it doesn't matter what it is. And then the base just advances it or delays it, and then it's lined up, and then you go to the full slot. Okay, so you come in with a partial slot. The base advances the timing until it's right, and then you take the full slot. That way you make sure that you don't fall into somebody else's time. And then on top of that, there is some guard times between the slots just for protection. So in GSM they have channels of 200 kilohertz. So it's a combination of FDMA and TDMA. So in GSM you have separation in frequency, and then each one has 8 time slots. Okay, so Each channel has 200 kilohertz of bandwidth with 8 slots. All right? So you can work out, using this example, how many users you can fit in 25 megahertz. Okay, so we've seen FDMA, we've seen TDMA, and now we go to CDMA, which is what Verizon uses. So in CDMA, all the users occupy the same bandwidth all the time. So the only way to separate them is because of the spreading sequences. Okay, so each user has a different spreading sequence. So when you come into the system, they assign you a spreading sequence, which is different from the other guys. And thanks to that, you can actually discriminate who is who. Okay? Now the spreading codes can be orthogonal or non-orthogonal. So the way it works is in the downlink, because all the signals are synchronous, you use orthogonal codes. Now, how do you build orthogonal codes? Well, usually they're taken from the Walsh-Hadamard family of codes. And here are some examples, right? For 2 users, the codes, of course, this is a very simple case for 2 users, but sorry. For 2 users, there are 2 codes, which are 1, 1 and 1 minus 1. Okay, so how do you see the orthogonality, right? Well, multiply the first 2 in the two digits. You get 1 times 1 is 1. Multiply the second. 1 times minus 1 is 1 minus 1. You add them up and you get 0. Okay? So now, how about 4 users? Well, now you need codes of 4 digits, right? So you have 4 codes. 1, 1, 1, 1, 1, 1 minus 1 minus 1, 1 minus 1, 1 minus 1, and 1 minus 1 minus 1, 1. You take any two of those codes, multiply them out, digit by digit, add up the 4 numbers, and you get 0. Okay, guaranteed. So if you had 8 users, you have codes of 8 digits. And actually, you can build a tree whereby you can build codes that are orthogonal using this pattern for any power of 2, right? So 2, 4, 8, 16, 32, 64. So if you would build that tree and you get to 64, that's what Verizon uses. They use exactly these codes for this family of codes for the 64 dimension. Yes?
In today's kind of system, right, DNA, you take the signal, multiply by the user random sequence, and then it's multiplied by the...
Yeah. So what happens is, yeah. So you're going beyond what I'm explaining, right? So they overlay 2 codes. There is a pseudo-random code and the orthogonal codes, right? But the pseudo-random code is common to all the users. So the separation of the users is based on the Walsh-Hadamard only. Right? So all the signals are multiplied by a pseudo-random code, which is different for every base station. For at a given base, it's common to all the users. Each user, no, in the downlink, each user has a different Walsh-Hadamard code, and they all have the same pseudo-random sequence. Now, the pseudo-random sequence changes from base to base. That's how it is. But the user separation within a certain base is based on these Walsh-Hadamard codes. In the downlink, the downlink. So in the uplink, there is no attempt to make the codes orthogonal. And the reason is that synchronization is very hard. So even if they were orthogonal, you couldn't get them lined up sufficiently well to get them multiplied properly lined up. So they just give up on it and they go with the non-orthogonal codes, which are the pseudo-random codes, just for their convenience. But synchronization is just too hard. I mean, you couldn't get the timing right because of the range differences to get the codes exactly lined up. So they just don't even want to try. So they use non-orthogonal codes. And one's got to be careful because you have issues with guy that is close to the base, guy that is far from the base. Even if his interference on you is very weak because his code is almost orthogonal to yours, or vice versa, right? I receive signals from him and from you, right? And yours is very strong because you're right here. His is very weak because he's far. The codes are not exactly orthogonal. They're pseudo-random, so they're almost orthogonal, but not exactly, right? So there's a bit of interference between the 2 signals. Even though it's a small interference, because your signal is so much stronger than his signal, you can actually kill his signal, right? So you got to be careful. So what they do is they use power control. So they actually power you down and they power him up so that this doesn't happen. So it's pretty sophisticated. Okay, that is it for CDMA. Comments? Other comments? Questions? Doubts?
they're going to collide, right?
They always collide, yes. Yes, so there's always going to be some leakage between the users. And that's why it's important to get the powers at the right levels. So the guys that are close to the base are told to power down. The guys that are far from the base are told to power up. Right? The base sends control channels, control messages, every half a millisecond or so. And they're going to power you down as you get close to the base. As you get far, they're going to power you up. So that the signals are received at about the same power, all of them. Right? Because otherwise, since they're not orthogonal, not exactly orthogonal, they could, yes?
If they're between these two branches connected, is there a trade-off of power?
Yeah, this is essentially you're asking which is the best, no? In some sense.
One's better.
Yeah, this is Pandora's box because this was for 10 years the object of huge political battles between companies, pushing companies that push different standards. So in the 90s, this went all the way to legal suits, multi-million-dollar fights between companies because Qualcomm used to make claims that CDMA was better than the other technologies, and then the competition said that TDMA was better, and so it was never quite resolved, although people are very opinionated on this. So you can ask whoever you want and you get different answers. If you want, I'll give you my answer during the coffee session later. Well, everyone's doing CDMA, but for the third generation. For the fourth generation, everything is going OFDM, which is again orthogonal. So at the end, it's a wash, I think, really. But this was the object of a very strong controversy between the experts, supposedly. So, papers were published making claims in one direction, then counter papers by other people, like Viterbi published his own papers, claiming, quantifying why CDMA was better, favored by other professors from other universities, why actually the other, was the way around. And people were making different assumptions in the papers. That's why papers were all right. They were comparing apples and oranges, and it's a very fascinating issue. Yes? Well, when they're pseudo-random, it doesn't matter, because what happens is that these pseudo-random sequences are designed so that it doesn't matter what the alignment is. They're always quasi-orthogonal. It means that they're never orthogonal, but they always have very low correlation. Right? So there's some sequences that are called gold sequences, which have this property, right? It doesn't matter what chip you add to them in time. They always have very low, never zero, but always very low cross correlation. So, in fact, I think there's some patents that protect these sequences, some of these old sequences too. So, it is very important, of course. But fortunately, the sequences do exist that have these good properties. So it works out. Otherwise, it would be a nightmare because you would have you couldn't get all the users lined up properly. So the only way is to make sure that whichever the timing they have, the interference is always manageable. And that's how they do it. It's a good point. Other comments? Okay, so we talk about SDMA now, very briefly. This is something very new. It hasn't, just sort of been discussed now for implementation. Here you use direction and angle to get channelization as opposed to time or frequency or code. So there's a picture on, 14.5. Okay, here it is, right? That's the idea, right? You have a bunch of users, and you use directive antennas, right? So you have an antenna pointing this way, one this way, and these users use the same frequency, the same time, the same codes, everything the same, except that you differentiate them because of their direction, right? You use directive antenna that just gets energy from that direction, and then another user is over there. You got to be careful not to get them mixed up, right? When they get too close to each other, you have to put them in different frequencies or something, right? So this is more of a complement, really, than a pure multi-axis technique. But it can be quite powerful. Okay, it requires directional antennas, and in its most rigid form, it just boils down to sectorization. You just break up the cell into 3 or 4 sectors, and then that's it. Now, it can be more adaptive, whereby these beams are actually following the users, right? So actually, it's a very interesting research topic. You have these beams that track the users as they move, right? So a beam tracks the user and tries to avoid the other users, and then a separate beam tracks the other user. And each beam tries to track a user and then put zeros in the other user so that there's no interference, that kind of thing, right? It's really beyond the scope of the course, but it's kept a lot of researchers busy for quite a long time too. And this is always used in combination with hybrid schemes, because if there are 2 guys that are in the same direction, you cannot possibly separate them using antennas. So then you have to put them in different slots, different frequencies or something. So it's just more of a complement. Yes, there are issues with handoff. In fact, with sectors, right? There is handoff from between sectors. Yeah, definitely. In fact, and in this case, if the beams track you, then you don't have to do that. But you can have beams crossing and things like that, right? But if the beams are fixed, definitely, once you step out of the beam, you're handed off to another beam, another sector. And this is problematic because you have very frequent handoffs. They become very frequent, and the overhead is pretty significant. So that's a drawback, actually. In fact, you don't want to have too many sectors, because at some point the handoffs are just too many. People just they move, a few meters and they have to be handed off. So it's very annoying for the system. Okay, so that was the multiple access, right, for persistent access. Now we'll talk about random access and scheduling, and that's going to be the last topic of today. So these are tailored to burst the access, and very important, this is what's used for initial access, right? So imagine that you turn on your phone was off, you turn it on, right? What does it do? Well, first it listens, right? It finds a control channel of the base station that's around here in Colombia. And then at some point it has to report, right? It has to inform of your presence here to the base and get registered to be able to operate. So you need to make a random access, because the base doesn't know you're here. It doesn't know that you exist. You just came here, you open your phone, and you have to make an access which is not expected by the base, right? So that's a random access. So in random access, you may have a pool of users that's very large, right? And just, they're not very active. So you can have, in this area, you can have, 1,000 people with phones that are turned off. Then somebody turns it on, and that user has to access the base station. So you have to make a random access. There's also scheduling, which is a centralized approach. So in this case, you have, channelization in time, frequency, code, space, same thing we just saw. But you don't get it all the time, right? For example, imagine you have time slots, but you don't get to come in every 8 slot like in GSM. The base tells you when to come in. So you make a request, and the base tells you, okay, now you can get this slot, and then you use it, and that's it, right? So the base can actually assign you a slot for just one use. That's called scheduling. So these are all useful notions. So scheduling, that's all I'm going to say. But random access, we're going to talk now for a few minutes. So random access is not centralized in the sense that the base doesn't even know that you're here. Yes? Yeah, no, it's a very interesting topic, scheduling, but we just don't have time to cover it. Yeah, I'm not saying that it's not. It is a very interesting topic, but it's just beyond. This is an introductory course. So if there was ever an advanced, I'm hoping that at some point I'll institute, and I've been asking for, all these topics could be covered, but unfortunately that's all we have. So random access essentially means that the base doesn't expect you, doesn't know you're here. So how do you access a base that doesn't know you're here? There are a few ways: ANOHA, Snotted ANOHA, and CSMA. Now, as you can imagine, ANOHA was invented by the University of Hawaii, right? That's not hard to guess. It's a very popular technique. It's very simple, actually. So in ANOHA, you have a packet to send. You just send it, right? That's it. So what happens if 2 guys send packets at the same time? Collision. So they're both lost, and that's it, right? So it doesn't get any simpler, right? Now, you can actually work it out, and there's an optimum load. So the load is the product of the frequency of transmissions, so number of attempts, access attempts per second, times the duration of the packet, right? So this is attempts per second, and this is seconds, right? Packet duration. So the product is something called the load, and it's a number between 0 and 1, essentially. So it's a percent. It's the percent of the time that the channel is used. So it's an optimum load. Below that optimum, the channel is often too idle, right? So nobody's attempting transmission. Above the optimum, there are too many collisions, right? So you can actually work it out very nicely. And what you find is that the optimum is 18%. So it is optimum to have an access of a load of 18%, which is very low, right? So it means that 80% of the time, somebody is trying to access the channel. So that's the optimum. So it's obviously a very inefficient technique, but it's very simple. So that's the trade-off there, right? High inefficiency is the price of simplicity. Now, the main problem with an hoja, of course, is that users can start transmitting at any time. So you can have these partial overlaps, right? You have a guy, okay, this is a typical situation, right? A guy sends a packet, right? Somebody else sends a packet at the same time. Just here, right? You just clip, I don't know, 10% of the packet. But that's enough. The packet is lost, right? So an obvious way of improving on an hoja is to have slots. So what you do is you take your time and you slot it. And you say, okay, guys, you can access the channel, you can try to access whenever you want, but only on the beginning of a slot. So that way you don't have partial overlap. You have full overlap or no overlap, right? So you avoid all these situations. So you just get, you get things lined up essentially. And this is the premise behind slotted an hoja. So you can only start transmission at the beginning of a slot. And so there are no partial overlaps. And the throughput actually, the load actually doubles. So the optimum load goes from 18% to 36%, which is pretty good. I mean, you just double, just by making slots in time, to double the load. But it's still, it's still about 1/3. So it's still pretty inefficient. And it needs synchronization, right? Because now the guys need to know when the slot starts. So we're back to the synchronization problem. So it's partially a solution, yes. Yeah, no, that's a good point. You mean, so the base can tell because it cannot decode anything. It gets interference, right? It gets two signals that are, like the code words don't make any sense, right? Now the transmitters, right? How do they know? That's a good point, right? So if you send something, how do you know it was received or not, right? What happens is that you get something called an ACK or an ACK from the base. So you get like a 1-bit message. So you get an acknowledgement or a non-acknowledgement. So usually if you don't get anything, it means it was lost. If you get an ACK bit, it means it was received, right? But it's a good point. I mean, you need to find a way to know if it was received or not, definitely. Okay, so the most elaborate way of doing random access is using CSMA. Okay, so that's how things are usually done. So what you do here is you listen before you send. Okay, so you listen, and if somebody else is using the channel, you just back off. Essentially, you just stay away, and you wait. Now it's very important that if you sense the channel is busy, you wait a random time before trying again. That's very important. Otherwise, you get huge problems, right? Like, as soon as the channel becomes free, 10 guys jump on it, right? So you have this random backup. That's what they do. That's what they do in Wi-Fi, right? In Wi-Fi, they use CSMA. And if you're a hacker and you know how to access the protocol, you can actually change this and remove the random backup and put it to 0. And everybody waits a random time except for you. So you always get the channel. Right? So you can. So if you're a good computer science guy, you can actually, you can have a room of people with laptops, and you're the only one that's getting access all the time. So if that happens to you, you get suspicious because these random access is supposed to prevent that and make sure that there's fairness between the people. But hackers are known to tamper with the protocol. And you can have that, 10 guys in the room, same computers, but only one gets on all the time. Right? This is why. Anyway, the random way precludes, several users from jumping on at the same time. And this is only effective, of course, if the users can sense each other. Otherwise, the whole thing doesn't work. So CSMA, sorry, is there a typo somewhere? No. Oh, yes, you're right, thanks. CSMA. Thank you. So in wireline, local area networks have these features, and so CSMA is how Ethernet works, essentially, right? So all the computers that are wired in the campus, for example, use CSMA. Now in wireless, there are two big problems in CSMA. One is the hidden terminal, the other one is the exposed terminal. These are classics of wireless. So hidden terminal. So say we have an obstacle here, I don't know, a building or something, right? And you have two guys, A and B, that want to talk to receiver C. Now A and B are blocked, so they cannot hear each other. Okay? So what happens is user A starts to transmit a packet, then user B listens as he's supposed to do, but doesn't hear anything because he's blocked from A. Right? So he sends his own packet, which collides with A's packet on C, and so the packets are lost. Right? So in this case, the premise CSMA didn't work because A and B could not hear each other. Okay, so that happens with some frequency, and it's a big problem in wireless. In fact, in Wi-Fi, this is an issue. Now, more refined is the exposed terminal problem. Okay, so let me take you through it. Say that user A wants to communicate with user B. Okay? At the same time, C is talking to D over there. Okay? What happens is that the signal that C sends to D actually interferes, gets also to A. So A senses the channel is busy. In reality, his channel to B is clear. So he could send the signal to B, and it'd be all right. But he thinks the channel is busy, and so he doesn't send it. So it's kind of the opposite of the hidden terminal. Okay? Now, there's a footnote here, because had A actually transmitted his packet, it would have gotten to be okay. But possibly he would also interfere with C and D. Okay? So this is a more complicated situation. But it's somewhat the inverse of the hidden terminal. Okay? So these are two classical problems. And how do we get around them? Essentially, the main way of doing it is by using the four-way handshake. So what you do, and actually that's what they do in Wi-Fi, right? That's how Wi-Fi works. You want to send a packet, first you listen. If you sense the channel is free, you send a request to send. A very short packet, just a few bits with your ID, which is an RTS, request to send. Okay? Now the receiver, if ready, replies with a CTS, clear to send. Okay? Which authorizes you to send, and actually it sends a CTS with your ID. So it sends you a clear to send. Okay? So if you're somebody else and you hear the CTS, you know that you're not supposed to talk. So you're quiet. Also, if you hear the RTS, you're also supposed to be quiet. Okay? So there is one way, two way, and then three way. You send your actual data, and then the fourth way is that you get an acknowledgement. Okay? So that's the four-way handshake. So users hitting an RTS or CTS that's not for themselves should refrain from transmitting. And again, there is a random backoff to avoid several users jumping on the channel once it's become free. Okay, so it's a very simple way, but it's very effective. And this is how, for example, Wi-Fi works. There's another way that's used in some other applications, which is the busy tone. So essentially, there's a separate channel in which you have a tone indicating you're busy or not. So it's like a flag. You put the flag up, you're busy. You put it down, like a taxi type of thing, right? But the four-way handshake is really much more popular. Questions here? Comments on random access? Are the notions clear at the descriptive level? All right. So that's all. End of the course. Now, before we go to the coffee, those of you who want to join me, I suppose you want to ask me about the final. So, okay, next Thursday, there's no lecture, but I'll be here in the afternoon. If you want to come in with some questions, you're welcome to do so. I'll be upstairs. Then in 2 weeks, we'll have the final, usual of the lecture, usual place. We'll make sure that there's no issue with time this time. So plenty of time, so you don't get stressed about the time. Okay. There is the. Okay. Yes. So let me speak about that a little bit in terms of topics. Okay. So it's going to be centered mostly on what we saw after the midterm. Okay. So especially modulations and coding, but also keep handy the stuff on propagation, especially the shadow fading. Okay, because there may be some combination of problems where you have to do, modulations with some shadow fading type of things, like within some homeworks, okay? Like coverages at certain error probabilities. So that stuff should be handy, the propagation. The information theory, I don't think is going to come in here at all, okay? So you can, so I don't expect any problems on information theory. But the propagation part, especially the shadow fading part, have it handy. And then what we saw after the midterm, modulation and coding. What we saw today is just descriptive, so there may be some notions there, but as you saw, there were no formulas here. So, I cannot possibly ask you a specific problem of this. It may come as an ingredient or something, but mostly it'll be modulations and coding. Any questions about the final? Specific questions? You can email me during the next 2 weeks if you have any questions or. Any other questions here? Yeah. Yes. Open everything. Bring a calculator, please, or a computer or something as the last time, okay? Just for simple math. I don't know, but it should be 4 or 5. It depends if they're short or long, but I haven't put them together yet. But anything else? Yes. FSK modulations. Actually, they use them in GSM. Yeah, GSM uses something called GMSK, which is a variation of FSK. So the reason is bandwidth efficiency. So FSK is bandwidth inefficient, essentially, because it's nonlinear. So, for example, a GSM channel uses 25 kilohertz for a voice call, right? A CDMA channel uses about 10 kilohertz for the same voice call, because it uses QPSK, right? So the main reason is bandwidth efficiency, but there's a nice advantage of FSK, and which is the reason that GSM chose FSK, which is the power efficiency. So the amplifiers are very cheap because they're nonlinear. So this used to be a big thing, right? The handsets were cheaper in GSM because the amplifier was a nonlinear amplifier, which are cheaper. I guess by now the cost has been coming down, so it's not that much an issue anymore. Or it's become a minor issue. So instead, the cost of bandwidth has just skyrocketed. So the trade-off between power and bandwidth has shifted very much towards being bandwidth efficient now and not so much power efficient. So everything's gone to QPSK and the such. But when they designed GSM, they looked at it very carefully and they chose FSK essentially. I mean MSK, but it's a variation of FSK. So it's good. It's a good point. Other comments, questions? Nothing? Okay, so those of you that want to come by, I'm going to go drop my laptop. I'll be in 5 minutes in the coffee shop. Okay, you're welcome to come, and it's my treat.